Hello viewers, welcome to this lecture on programmable timer counter. You will find there are many applications in process control instrumentation and embedded systems where you have to generate clocks of different frequencies, delays of different durations and strobe signal after certain interval. These type of signals are very common in these type of applications. And in this lecture, we shall discuss how these signals can be generated by using different techniques, software based, hardware based, and then some combined approach. And we shall see how a programmable timer counter device can be used very efficiently for this purpose. First, let us consider the software based approach, where we shall be using a port line connected to the microprocessor. Here is your microprocessor. Microprocessor is connected to a programmable I/O chip. Let it be 8255, and it is connected to the system bus. And how this interfacing can be done is known to you. And as you know, 8255 has a number of port lines. Now, suppose you want to generate a clock on PA0 port line of 8255. What you can do? You can configure port A in the output direction. Then you can generate you can make it high, then generate a delay of some duration. Then you can make it low, then generate delay of duration, say this is T1, let this duration be T2, and then you repeat this duration T1 delay. In a loop you can go. So this for this duration duration T1 you then make the line high, for this delay duration T2 you make it low. So in this way you keep on generating in a loop. With the help of two delay routines you can generate a clock having time period T is equal to T1 plus T2, where T1 is the delay duration when this output is made high, and T2 is the delay duration when this output is made low. And you know how these delay routines can be written to generate, for a particular time period. So this is how you can generate a clock. In a similar manner, another port line can be used, say PA1, to generate a delay of duration T. So you make the say PA1 port A, you configure it in the output direction, make this line high initially, then you make it low, then you generate a delay of duration T, and after T you make the port line high. This you can do with the help of a program. So this is how you can generate a delay of duration T, and after this duration this line can be used for various purpose, say to generate an interrupt or various other purpose. Similarly, you can make use of, say, port C0 line to generate a strobe signal after some duration. So this type of clock generation, delay generation, strobe signal generation can be done by programming with the help of some port line. However, it has some limitations. Let us try to understand what are the limitations. First one is the microprocessor remains busy whenever it is doing this kind of delay generations. What it is doing? It is running a program in a loop. Obviously, it is kept busy for this mundane job of generating only a clock. It cannot do anything else. Similarly, whenever it generates this delay period, the microprocessor also remains busy. And so apart from microprocessor remaining busy, there is another limitation. You can generate only one signal at a time. You cannot generate three such signals at a time. That may be required in some applications. You may have to generate clock, you may have to generate delay simultaneously. Obviously, this cannot be done. So although this is flexible, You can implement everything by program, but because of these two limitations, this particular mode is not very popular or widely used. So, the next approach is to use purely hardware based approach. A purely hardware based approach can be implemented by using suitable device like 555 timer. This is a 8-pin integrated circuit chip. It is very versatile, but since it is hardware based, all the functionality has to be implemented by suitable interconnection, hardware interconnection. Just to give some idea about how you can implement a clock generator or a delay generator, let me explain briefly the operation of this very popular chip. You have got two comparators. As you know, in case of a comparator, inputs are analog in nature, may be analog in nature, and output is digital. And for a comparator, when the positive input is higher than the negative input, then output becomes 1. So is true for the lower comparator, and to positive input of the lower comparator and the negative input of the higher upper comparator, there are 3 resistors, 5 kilo ohm resistors, which are precision resistors, laser trimmed, very accurate. And as a result, if you apply a voltage VCC here, then you will get 2/3 VCC voltage here and 1/3 VCC voltage here by simple Ohm's law. And these comparators are driving a SR flip flop, set reset flip flop, and the S input is connected to upper comparator, R input is connected to the lower comparator, and the output of the flip flop is available here, Q and Q bar. Q bar is available as output. However, Q is used to drive another transistor through a resistor, and this transistor output is designated as discharge. So you see different names are given based on the use of these various pins. The 6 is known as threshold pin, 5 is known as control pin, 2 is known as trigger pin, 4 is known as reset pin, which with the help of which this flip flop can be resetted. 3 is output pin, where output can be obtained, taken from where output can be taken, and this output is discharge pin. You will see this, you will use this transistor to discharge capacitors. So let's see how this popular 555 chip can be used to generate clock. The operation is known as astable operation. You may have known, you may be aware of the astable multivibrator, which is used to generate clock. Here, this 555 timer is used to generate clock. The way the interconnection is done is shown here. Here you see we have used 4 additional components, 2 external resistor RA and RB, and a capacitor C, and another small value of capacitor, say 0.01 microfarad. And let's see how it operates. As it is shown here in this diagram, the pin number 7, which is the discharge pin, is connected to the junction of these 2 resistors, and 2 and 6, this comparator pins are tied together and connected to the junction of this capacitor and resistor, and the 3 is available as output. Let's see how it operates. Initially, when the power is turned on, this capacitor was in discharge condition, and so since it is in discharge condition, what will happen? Since this value is 0, you see the capacitor input is available here. Since this is 0 and this voltage is higher, obviously this output will be 1, and this will reset this flip flop. This will reset mean here you will get 1. Reset means this will be 0, this will be 1. So this transistor is off. So you will get 1 at the output 3, but as the charge on this, as the capacitor charges through RA and RB, it reaches initially VCC by 3 and then 2 VCC by 3. When it reaches this level, 2 VCC by 3, as it is connected to the pin number 6, this particular comparator turns on and output becomes 1. So that sets this particular flip flop. and when it sets this flip-flop, the output goes down as it is shown here. And not only the output goes down, this line becomes 1, and which makes this transistor on. This transistor on means that this transistor is now on, and as you can see, this is connected to this point. So now earlier it was charging. Now what happens whenever this is connected to effectively to ground, because this transistor is on, now the capacitor discharges through this resistor RB. So as it discharges, the output remains in low values, and again it reaches that with the 1/3 level, it goes below 1/3 level here, then this transistor, this particular comparator turns on. So as you can see here, again the charging starts, and after that this capacitor keeps on discharging and charging, discharging and charging between Vcc by 3 to Vcc by 2, and at the output you get a clock signal, and the frequency of the clock signal can be derived as 1.44 by Ra plus 2 Rb into C Hertz. Okay. So capacitor in farad, resistance in ohms if you give, then you will get frequency in Hertz. So this is how you can generate a clock with the help of 555 timer. Now you can use the same chip, however you have to change the hardware interconnection to generate a delay. Here the delay period is shown here. This delay you would like to generate. How it is interconnected? Here you see the 7 and 6, this is tied to this and connected to a capacitor, and there is a separate resistor which is connecting to it. Now whenever and there is a input trigger, 2 is acting as a trigger input. Here 2 is acting as a trigger input. Whenever you apply a high voltage signal, say Vcc, then this output is higher than that. This output is higher than that means what will be the situation here initially? Initially this is Vcc and this is low. So output is 0, and as output is 0, this transistor is off, and what will happen, here you will get, it is taken from the pin number 3. Now the capacitor starts charging, and as it reaches 2/3 Vcc, 2/3 of Vcc, again the same thing happens. This turns on, and that means this output becomes 1, which sets this flip flop, and when it sets this flop, this line become 1, and you will get this transistor turns on and discharges the capacitor, and it remains in that state until another strobe comes. So it is driven by this trigger. As a trigger comes, as it happens in case of monostable multivibrator, after that trigger point, this edge, it will generate a delay of duration t, where t is equal to 1.2 RCC. So you see, in this case, using the 555 timer, you can generate clock, you can generate delay of some duration in the monostable mode, but you have to change the interconnection. But if there is no need for the microprocessor to remain busy whenever this timer chip is generating clock or delay. So this has some advantage, but the disadvantage, the operation can be controlled only by changing the hardware interconnection. So if you want to change the frequency, you have to change the value of the resistors or capacitors, or if you want to change the delay of duration, then you have to change the value of this capacitor or resistor. Everything has to be done by changing these capacitors and resistors that you are connecting. And on the other hand, in software case, we have seen that it is very flexible, but the microprocessor remains busy. So can we achieve best of both the worlds? The advantage of both hardware based approach as well as software based approach. That means we should have the flexibility of programming, By programming, you can change the configuration, the operation of the circuit. At the same time, the microprocessor will not remain busy for doing this mundane job. And that can be done with the help of some special IC, and which is essentially a combined approach. You can say it is combined approach. In this combined approach, what you do, we make use of a special programmable device known as 8253 timer counter chip. And this can be interfaced to the microprocessor the usual way. This goes to the system bus of the microprocessor. You can see these lines will go, and you have to use some decoder circuit to generate this particular chip select signal. Otherwise, these signals will directly come from the microprocessor, as you already know. The data lines, read, write, A0, A1, and only the chip select has to be generated with the help of some other address lines and the IOM line. And that's how you can map various registers inside the 8253 programmable timer counter chip. Let us see what is inside this programmable timer counter chip. The internal block diagram is not much different from any other programmable device. It has got a data bus buffer where the tri-state buffers are there. Then there is a read write logic which controls several registers inside the chip. You have got only 4 registers. One is control word register, which is very vital, and by programming this you can configure the mode of operation, and you have 3 16-bit registers which can be used as counters, and these counters can be used to generate clocks, delays, and various other things. Let's see how it can be done, and to do that you have to understand how these registers can be accessed. This diagram shows how the registers can be accessed and what are the different formats for the mode control register. Obviously, for accessing the registers, the chip select line has to be 0, and depending on the values of on A0 and A1 which are connected here, A0 and A1, you may connect A8, A9 as well, because these are mapped on the IO address space. Both A0 and A8 has the same value. Now, whenever chip select is 0, A1 is A0 is 0 and A1 is 0, it accesses the counter register, counter 0. That means the counter 0 is accessed. You may be wondering how a 16-bit register can be accessed with the help of a single address. We shall see some trick is used here. Using the same address, you can access both the lower order byte and higher order byte of this counter 0. And whenever it is 0, 1, then counter 1 is accessed. Whenever it is 1, 0, then counter 2 is accessed, and whenever it is 1, 1, these two bits are 1, 1, A0 and A1, then you access that control register or mode control register. And of course, whenever the chip select line is high, you cannot access none of the registers. And this is these are the different bits of the mode control registers, D0 to D7. It is a 8-bit register, and these are the various bits shown here. The least significant bit is known as BCD. BCD stands for binary coded decimal, and depending on the value that you write on this bit, the count value can be given either in binary or in BCD. So you have the choice of using these counters to operate in binary mode or in BCD mode. That means they can work as binary counter or as decade counter. That means BCD counter, decade counter, as you know, divide by 10 counter. So this bit does that, and then M0, M1 and M2, that means D0, D1 and D3, these bits are used to set the modes. So you can see here there are 6 different modes of operations. If these bits are 0, 0, 0, then mode 0, 0, 0, 1, mode 1. Then if these two bits are 0, 1, irrespective of this bit, it is mode 2. Then you get mode 3 for X, don't care, 1, 1, and 1, 0, 0, mode 4, and 1, 0, 1, mode 5. So you have got 6 different modes, and in 6 different modes, each of these sections can be operated in different ways. So you see, you have got 3 different counters. Each of them can be operated in 3 different ways, and each section is provided with 3 lines. One is clock input line, another is gate input line, another is output line. So this is clock 0, gate 0, out 0, clock 1, gate 1 and out 1. So all the 3 are independent, clock 2, gate 2 and out 2. So using these lines and the counter register, different operations can be performed and in different modes that we shall see in detail. And then as I was telling that you have got 16-bit register, you are using the same address to access both the bytes, lower order byte and higher order byte. How it is done is explained with the help of these 2 bits. So these 2 bits, 0, 0 is used for a special operation known as counter latch, by the help of which you can read the content of the registers, these counters, on the fly when it is being decremented or incremented. So on the fly reading and reading is possible whenever these 2 bits are 0, 0. These counter latch bits are 0, 0. And whenever it is these 2 bits are 0, 1, then you can access the MSB. That means a most significant byte of any one of the counter values, that depending on the address here, counter 0, counter 1 or counter 2 can be accessed. You can write or read with the help of this, whenever you write 0, 1, then MSB. And whenever it is 1, 0, then the lower order byte can be accessed of any one of these counters. Similarly, if you want to access LSB followed by MSB, first lower order byte, then higher order byte, most significant byte, then you will write 1, 1. So you see, you can access either the lower order byte of any of these registers, higher order byte of any of these registers, or you can access lower order byte followed by higher order byte. And this can be done by writing suitable values in these 2 bits. Then SC0 and SC1, these 2 are used to access. You have seen that there are three independent timer counter sections, but here only one control register is shown. But inside the chip there are 3 control registers. Obviously, there should be 3 independent control registers for each of them, because they can operate independently and simultaneously. So to do that, you have to program all the 3 control registers separately. This is being done with the help of these 2 bits. That means whenever these 2 bits are 0, 0, control register corresponding to counter 0 is accessed. Whenever these 2 bits are 0, 1, then control register 1 is being accessed. Whenever it is 1, 0, then you are accessing the control register 2. And of course 1, 1 is illegal, you should not put 1, 1 here. And these are the format of the mode control register. So you can see here, this particular register plays a very important role, not only in configuring the different sections, this one or this one in different modes, but by using these 2 bits you can access different registers, the counter register and control registers. let us see the operation of this device in how they operate in 6 different modes. In mode 0, is known as interrupt on terminal count. This stands for terminal count, interrupt on terminal count. What you do here? This is the clock that is connected to any, suppose you are considering this timer counter section 0. You have to apply a clock here, and maximum clock frequency is 2 megahertz. Maximum clock frequency is 2 megahertz. So you have to apply a clock, and then if you apply if you use a out instruction to write some value into this counter, which is shown with the help of this write signal. By write n, that means n has been written in that counter register. Whenever you write n in the counter register, after that what it does, from the next clock it keeps on decrementing. Suppose you have written n is equal to 3, then at this age, say, so this is, here it is 3, then at this age it will become 2, at this age it will become 1, at this age it will become 0. So in this way that counter will act as a countdown register, and here it will reach terminal count. And as you can see here, as it reaches the terminal count, the output goes high. So at this age the output will go high, and this name has been given to it, interrupt on terminal count, because this line can be used to interrupt the processor. So this can be used to interrupt. It can be connected to any one of these inputs of the microprocessor, 8085 microprocessors. And as you know, the interrupt inputs are high active, so it can be directly connected to any one of the interrupt lines, and the processor can be interrupted. Now we have seen the operation of the clock input, where you have to apply a clock, and on this line out you are generating the this particular signal, which is used to interrupt on terminal count. What is the role of this input, gate input? With the help of this gate input, this countdown can be inhibited. So whenever this is connected, so here it will be 3 decremented by 1, but since this line is low, then this countdown will not take place. So here it will become 2, then it will become 1, then it will become 0. So this is how then it generates the terminal count. So you see, the gate is inhibiting the clock to decrement the counter, and that is the function of the gate. And if you connect it to VCC, then of course then it simply counts down and interrupts the processor on terminal count. So this is the operation of the device in mode 1. And what is the application of this? You can use it to generate the microprocessor after some time. Suppose you generate a delay period and you want the microprocessor to be interrupted after that delay period. So you can find out some value to be written here into the counter, either in BCD or in binary you can write, and then after that it will keep on counting down, and since this is a 16-bit register, that total number can be 64K. So after a very long time the microprocessor can be interrupted, and after this writing is done, microprocessor will keep on doing its own other operations. It will not remain busy for anything. So microprocessor is freed after that, but it is interrupted on terminal count. Let us see the second mode of operation. In the second mode of operation, it is known as hardware retriggerable one shot. As its name suggests, that just like monostable multivibrator that we have seen in case of your 555 timer, there we have seen that there was a trigger signal which was used to trigger the monostable multivibrator, and after you trigger, then it generates a delay. Somewhat similar operation is realized in this particular mode, in this hardware retriggerable one shot. Let's see how it is being done. As usual, you have to apply a clock to the clock input, then you apply a trigger signal, and after you apply a trigger signal, let's assume the value that you have written n is equal to this is for n is equal to 3, and after this trigger comes, it will start counting down 3, 2, 1 and 0, and after it reaches terminal count, the output goes high. So as you can see here, the operation is same as this one. It generates a delay. So you are achieving the same thing. Now suppose after this first trigger was generated, it goes down and again another trigger comes. It is being triggered at this low to high edge. So if another edge comes after that, what will happen? Actually, it works as a retriggerable mode. What is retriggerable mode? At this edge again this value becomes 0. So it was 3, 2, again it starts counting down from 3. This gets retriggered. So 3, 2, 1 and 0, then it goes high. So you see it can, if another trigger comes, again it will start afresh. The same thing is also done here. I mean in hardware operation, it can be retriggered and again delay will be increased. Anyway, let us consider the 8253 timer counter. So here it acts as a hardware retriggerable one shot. That's the, and how the retriggering occurs, that is explained here. And the trigger input, where do you get the trigger input? That gate acts as a trigger input. So gate line is being used as the trigger input. You are applying clock here and you get the output from any one of them. I am showing for this section, it is all the three can be programmed for any one of these modes. This is mode 1. Then comes the mode 2. In mode 2, it acts as a rate generator. What do you mean by rate generator? If you write n, then it keeps on generating a strobe for every 3 clock periods. For example, here you have written n is equal to 3. Then as you can see here, this is 3, 2, 1 and 0. So for this 0th clock pulse, it goes low, and again 3, 2, 1 and 0. So this is the rate generator. You are generating, and this will keep on generating a strobe, a pulse of duration 1 clock period when the countdown occurs for the 0th value, and again the register is being reloaded with the same value internally. You don't have to do it yourself. Automatically the n value of n is reloaded, and again it's counting down, and whenever it reaches 0, another strobe signal is generated. So it goes on this way, and this is the rate generation. Then you may be asking, what is the role of this gate input? This gate input can be used to reset. Here the function is known as reset. What it does, whenever this line is low, again you can see here it gets resetted 3, 2, 1 and 0. Maybe it was say 0, 3, 2. It started decrementing. This is 3 and 2, but again it starts afresh 3, 2, 1, 0, and again 3, 2, 1, 0, and so on. It will continue. So with the help of the reset, the count value can be resetted to start afresh, and after that rate generation will start. So that is the role of the reset signal, and the gate input can be used to function as the reset signal in this particular mode. This is your mode 2. Mode 3, is simple square wave generation, as you have done in case of your astable multivibrator. Here you write some value n. N can be odd or n can be even. Whenever n is odd, then suppose n plus 1 by 2, for that duration it remains high, that output will remain high, and n minus 1 by 2 duration it remains low. So this is the in case of odd. In case of even, of course, this is n by 2, it remains high. That means you will get a square wave whenever the value of n that you write is even, or and again for n minus n by 2 duration it remains low. So that is explained in this diagram. Here I have written n is equal to 3, let us assume. Since n is equal to 3, it remains high for 3 plus 1 by 2, 2 clock periods. So this is one and this is another one. So 2 clock period, and it remains low for n by 1 by 2, that means 1 clock period. So you see it is not a square wave but a rectangular wave. Now if the, let me show the output for n is equal to 4. In this case, what will happen? It will go high, it will remain high for 2 clock periods, it will then go low for 2 clock periods, again high for 2 clock periods, again low for 2 clock periods, and so on. So in this case you get a square wave. So depending on the value of n, odd or even, you are able to generate a rectangular wave or a square wave, but of course the difference in period is only of 1 clock period. Whenever the value of n is large, then this difference will not be noticeable. Suppose that value of n is 1000 or 5000, then one will be 5001, another will be 5000. I mean 2001 and another will be 2000, like that. So this may not be noticeable when this value is large, but otherwise this is how odd and even number is taken care of in this square wave generated mode. Now let us consider the software triggered strobe mode. As its name suggests, it generates a strobe signal at the output. It generates a strobe at the output, and and it is software triggered. How it is software triggered? After you write the value in one of the counter registers, it starts, this acts as a trigger. That means this writing operation acts as a trigger, and then it starts decrementing, say 3, 2, 1, then 0, and after 0 is reached, a strobe is generated, and then it remains high. So a strobe of one duration is generated when the terminal count is reached, and of course this operation can be delayed by gating. That means whenever the gate input is connected to low for some duration, then the output will be delayed, said delay duration. That means counting down was taken place 3, then for this duration it will be skipped, and here you will get 2, 1 and 0, and then it goes low for 1 clock period. So you are generating only one strobe, it is not repetitive, and this signal can be used to start some other some other applications. This can be used to say trigger a monostable multivibrator or anything you want. You can do many things by using this signal. The last mode of operation is hardware triggered strobe. Here in the previous case it was software triggered. The writing operation itself was triggering the strobe generation, but in this particular case it is hardware triggered. By hardware triggered I mean this gate signal, gate line is used as the trigger input. So gate line is used as a trigger input here, and as you can see, you have it is not shown the writing operation. Writing has been done, but there is no activity on the output. But as soon as a trigger is generated, then it starts decrementing 3, 2, 1, 0, then it goes low for 1 clock period. So in this case, the signal is getting triggered. It is the output. I mean, this counting down is initiated by this hardware signal gate input, and as you can see here, you get 3, 2, 1, 0, then a strobe signal. However, it can be re-triggered as well. Say it is triggered here, again it is triggered here. So counting down was 3, 2, then say 3, 2, then it started, 1 should have been here, but before that it has got triggered. So again it will start decrementing 3, 2, 1, 0, then a strobe will be generated. So here it is also acting as a retriggerable signal, hardware retriggerable strobe, but it generates only a strobe signal, unlike the previous case where it was generated repeatedly. Here it generated only once. Let me consider a practical example of 8253. Let us consider that we have a 8253 in a particular application. This is 8253, and you have got one 8251 also connected to the system. This is 8251, and let's assume the address assigned to this 8253 is based on these inputs, the decoder circuit, say A7, A6 are connected directly to this NAND gate, and A5 is connected through an inverter, A4 is connected through an inverter, and IOM is also connected to this input. So the address will be 1100, that means it will be the address will be C0, C1, C2 and C3 for this for the different resistors inside this 8253. And let's assume that we have to generate a clock for this 8251. As you know, 8251 has got two inputs, PXC and RXC, where clock has to be applied, and this is being generated by using 8253. And as you know, 8251, whenever it is used for implementing RS-232C, it can have several standard baud rates. These baud rates are 75, 110, then multiple of 75, 150, 300, 600, 1200, 2400, then 4800, then your 9600, then 19200. So these are the various baud rates, standard baud rates which are used. Let's assume the clock will correspond to this 19200, so that inside this chip, by programming, it can generate two more addresses. So one will be divide this by 16, that means it will get 1200, and also divide by 64, you will get 300. So 19,200, 1200 and 300, these are the baud rates which can be generated by using this 8251. But for that you will require a clock of 19200 to be applied. How it can be generated? Say to the, this is connected to the out input, not clock, but out input of the 8253, and to the clock input you have to apply some clock. This clock can come from the clock output of the microprocessor, And as you know, the clock output of the microprocessor has a clock frequency of 3.072 megahertz. Since the maximum frequency of 8253 is 2 megahertz, you cannot apply 3.072 megahertz to 8253. So you have to divide it by 2 to get 1.536 megahertz to be applied to the clock. Let's assume the gate input is connected. This is the gate input is connected to VCC. Now, by programming, you have to generate 19,200 clock frequency, and that has to go to this TXC input. How it can be done? You can program this 8253 in mode 3, as I have already explained. Mode 3 corresponds to square wave generator. And for square wave generator, if you program in mode 3, it will continue to generate clock in this fashion once the chip is initialized. And to do that, you have to program in mode 3. Let's see how it can be done. For that, first of all, you have to initialize the control register with some code. Let us see what code has to be written there. This is the control word format of 8253. This bit has to be 0 if we want binary. If this bit has to be 1 if we want BCD. Let's assume that the counter has to be BCD divider, binary BCD counter. So we shall make this bit 1. The mode will be mode 3. So let's assume it is 0, 1, 1 and 1. So the last 4 bit will be 7, 1, 1, 1 and 0, 7. Here you want to load the LSB followed by MSB. So this will be 1, 1, and in this case here, since you are using the control register, it will be 0, 0. So the code that you have to write is 0, 0, 1, 1, 0, 1, 1, 1, 1. That means the code is 0, 0, 0, 1, 1, then 0, 1, 1, 1. What is the value? MVI A37. This is 37. That you have to write into the accumulator. Then you have to output it to the control register. What is the address of the control register? Control register address, as you have found out, the various 4 registers. This is for register counter register 0, counter register 1, counter register 2, and this is for the control register. So the address will be out 3C. Sorry. C3. So C3 will be the address of the control register, and it is configured in mode 3, and it generates the continue to generate the clock, provided we initialize the control register. So to initialize the control register, what you have to do? In the most significant, first we have to write data into the least significant byte, followed by most significant byte. So in this case, what value you have to write? You have to generate 19,200 from 1.536 megahertz. So what is the value? 1.536 into 10 to the power 6 divided by 19200. This is exactly equal to 80 in BCD. So you have to write 80 into the control register. So first you have to write the least significant byte. So MVI A80H, that has to go to the control register 0. So it will go to the out C0. Then the another byte you have to write, the most significant byte, because this code corresponds to LSB followed by MSB. So you have to write MVI A00H followed by out C0. So once this writing is over, here you will get a clock, continuous clock of 19,200 generated. and apply it to this 825551 serial port chip. So you see, by writing this simple program, you are able to generate the clock continuously, and the microprocessor is free to do anything after this program is executed. After that, either you can put halt, or there can be another piece of code. It doesn't matter what is there. So with this simple example, we have seen how 8253 can be programmed to generate a clock, and it will continuously keep on doing that after a particular this code or initialization is done, and then the microprocessor is free. So this is the beauty of programmable IO chips. With the help of the programmable IO chips, we have seen that once the initialization is done, it keeps on doing the corresponding task independently without the intervention of the microprocessors. For example, in this case, the 8251 is doing the clock generation, and similarly in case of your 8251, for example, what the 8251 does, once you write the character here, the transmit buffer, just 1 byte, this 8251 is a serial port, will do the necessary framing. It will automatically generate the start bit, then it will shift out the data bit which is here, then it will generate the parity bit as it is programmed with the help of the mode register, then it will generate the stop bit. So it will continue to generate start bit, data bits, parity bit and stop bit without the intervention of the microprocessor, and the microprocessor is free for doing that. Similarly, when a character is received in the receive buffer, received through this RxD line, the start bit, stop bit, parity bit are automatically strip topped, and the parity checked whether the parity that is calculated is same as the parity that is being received, and only the byte, data byte is transferred to the receive buffer, and which can be read by the microprocessor. So students, we have seen how the programmable IO chips are so much useful. It not only relieves the microprocessor from the mundane job, and it also extends the flexibility of the entire system, of the microprocessor based system. So we have discussed a number of general purpose and special purpose programmable IO devices, and even now ready to design entire system based on the knowledge that you have already acquired and the background that you have, and with that you can build complete microprocessor based system using RAM, ROM and various type of programmable IO devices, either general purpose or special purpose. We shall discuss how you can design a complete system using RAM, ROM and various types of programmable IO devices in the next lecture. Thank you.